third speaker today is a member of the faculty, Richard R. Lunt. He's currently assistant professor, and his group focuses on understanding and exploiting excitonic photophysics and molecular crystal growth to develop unique thin-film optoelectronic devices. He earned his bachelor's degree in chemical engineering with honors from the University of Delaware. His PhD is from Princeton in chemical engineering in 2010. He worked as a postdoctoral researcher at MIT until 2011. His work has been featured in Nature, New York Times, Huffington Post, CNN, CBS, Bloomberg, and NBC News, among other places. His internationally recognized research has earned him a number of prestigious awards, including the NSF Career Award, the Camille and Henry Dreyfus Mentor Award in Environmental Chemistry, the DuPont Young Investigator Award, the GPEC Solar Innovation Award, the Undergraduate Research Mentor of the Year Award at MSU. He is the inventor on 17 patents, the majority of which have been licensed, and recently he won the Innovation of the Year Award at MSU. He's also a founder of Ubiquitous Energy Incorporated, which is commercializing a range of seamless light harvesting technologies and is currently valued at over $10 million.
Thank you very much for inviting me to be here to talk about what we do in our group. So our group really focuses on a lot of different areas. But primarily what I'm going to talk about today is what we think is a new paradigm for solar energy and for energy efficient electronics. All right. So I'm going to start with the kinds of materials that we're really interested in investigating in our group, and it spans everything from inorganic semiconductors to organic semiconductors. And so we have the organic semiconductors here on the left, the inorganic semiconductors, things like nanocrystals, colloidal quantum dots, and organic molecules on the right. And the molecules that we focus on are molecules that are in some way nanostructured or excitonic. And this is important because it leads to the potential to make low-cost electronics. And that's where most people have been interested in developing these materials. And they're interested in developing them for things like photovoltaics and light-emitting diodes. And we really want to push the materials properties and do something unique, something that you can't do with traditional semiconductors like silicon. And so that's really the focus of our group, is developing these unique applications that exploit the unique properties of the nanostructured features of these materials. So this is the primary breakdown of where the group focuses. We spend a lot of time understanding how to synthesize these materials, how to grow crystals of these materials, how to orient their crystal structure. And so this is just an example of some in situ electron diffraction that we do. We basically take electrons and shoot them at a surface and watch the crystals as they grow. So we understand the kinetics of the process. And so we start with our single crystal. We start growing an excitonic material on top of that. We see the diffraction pattern change, and we can learn something about the growth mechanisms of these materials. We then take that information and try to apply it to make these kind of unique applications. So we try to make devices that can convert light to electricity. So this is solar photovoltaics. And then we do the reverse. So if you take a PV, you can actually just run it in reverse, take electricity and convert it into light. And then we try to do something with that electricity. We either use it directly or we come up with applications to turn it into fuel or store that energy. So these are the areas that we really focus on. How many of you have a Samsung phone? Looks like maybe about a quarter. In the Samsung phone, they have an OLED, organic light emitting diode display. And this is really the future of the display technologies. This will eventually take over all displays, just a matter of time. And those molecules are exceptionally good, but they all contain platinum and iridium. And those are two of the least abundant materials on the planet. And so we're working on generating these kinds of architectures that are efficient and low cost for the next generation for things like lighting. So you can really make a big impact on the energy that we consume in buildings. About 20% of all the energy we use in buildings is used in lighting. And so this is actually the first demonstration of a nanocluster light-emitting diode. So this is something we're very excited about. And in the photovoltaics side, we're really pushing and to try to make these solar cells more aesthetically pleasing and make them so that you don't even know that they're there. Basically a transparent solar cell. All right, so that's what I'm going to talk about. I'm going to talk a little bit more about our focus on solar energy. The reason we're excited about solar energy is highlighted in this plot. If you look at trying to power the world with a renewable energy source, you have to appreciate how much energy we use. So the average rate of energy usage in the entire world is about 16 terawatts. And if you look at all of these renewable energy sources and you look at the total potential, so you take every river that there is in the world and you say you're going to put a dam on it, this is the total potential that you could get. So it's important, but it's not the entire solution. We're not going to power the world with hydroelectric. We look at wind, again, it's a more substantial fraction, but it's not enough to power the whole world. Biomass is very significant. This is an area that MSU has had a lot of strength, and this is an important stepping stone. This is something that we absolutely need to be working on. But as we go down the list here, we get to solar. And solar is actually off this scale. To get it to actually fit on this chart, we account for the fact that we're only going to use a solar cell that's about 10% efficient, and we're only going to cover 1 to 2% of the land area. Even taking that into account, there's enough solar energy to power the whole world. So we have the answer, right? We can go home, right? Not quite. So there are a lot of things that we have to overcome, but primarily issues associated with cost and aspects of deployment. And that's really what we try to focus on, making these new kinds of solar cells that are not only low cost in their modules, but are also low cost to install. That's really important. All right, and that's where this new idea for a transparent solar cell came from. When you walk around a big city and you see all the glass that there is, our original idea was if there was a way to turn that into a solar harvesting surface, you can suddenly have solar harvesting everywhere and not even know that it's there. And so when we started thinking about this, the idea of making a transparent solar cell seemed kind of like an oxymoron. If we're going to make it transparent, how are we going to get any power? And the answer is actually in the solar spectrum. If we look at the parts that we can't see with our eye, there's a lot of photon flux that we can harvest to produce power. So these are the parts of the solar spectrum that are visible to our eye, namely the near-infrared and ultraviolet parts of the solar spectrum. And so what we're going to try to do is make a system that selectively harvests those parts. And if we try to do this with the traditional semiconductor like silicon, we see that this isn't really possible because the absorption coefficient is basically flat across the spectrum. So if you want to make it transparent, you can't make it absorb. And so there's always this trade-off of making it transparent or making it power producing. Instead, if we look at these excitonic materials, we can make materials that have very strong resonances wherever we want them to be. And so we can selectively put these absorption resonances in the ultraviolet and in the near-infrared. And indeed, we've already demonstrated a full catalog of materials that can harvest deep into the near-infrared. And once we showed that we can actually make these structures, we showed that we can actually do something useful with these. We can make modules. We can make flexible versions of these. And so this is something that was very exciting to us. And so we ended up starting a company called Ubiquitous Energy Incorporated. They're out in California. And they're actually working on scaling up and commercializing this technology now. The one thing I'll highlight is the efficiency limits. What's interesting is if you take a completely opaque solar cell and make it completely transparent, you go from an efficiency limit of about 33% to about 21%. So there's a tremendous amount of potential in making this kind of device, and that's what our group really focuses on. So the idea is that we're going to install this on glass that's already being installed, or we have the potential to retrofit it as a laminate on the inside of a building. This is very important because if we look at the estimates that we have for how much glass is installed on a yearly basis, in the US alone, it's about 4 billion meters squared. If we translate that into a market potential, assuming that we're going to sell these at 10 cents a kilowatt hour, that's about $100 billion impact. So it's quite big. If we can even get a fraction of that, that's a huge market. And I recommend to any of the students in the audience, if you think of an idea where you see a market potential that big, start a company. Patent it and then start a company, okay? And that's only really one of the markets. You can start to think about integrating this anywhere where you want to produce power locally. You can think about using this in mobile electronics so that you have to plug your phone in less often or never plug it in at all. So there are a lot of markets, and each one of these markets is a very big market. We've also started looking at ways to even make this lower cost than it already is. And so in the 1970s, there were researchers that knew that solar energy was just too expensive. And so they started designing these luminescent solar concentrators. And the idea was, instead of using a large area of expensive solar cell, they were going to use a cheap plastic embedded with a colorful dye. And that dye absorbs some fraction of the solar spectrum, and then it glows at another wavelength in the visible part of the spectrum, and it gets wave-guided around to the edge, just like a fiber optic. So as you get it closer to the light, you can see the edge kind of coming out the side. And then we mount our solar cell just around the edge. And so we don't use a lot of the expensive solar cell material. And so we started thinking, this is a really low-cost thing. This is just a cheap piece of plastic. Is there a way that we can make the same kind of transparent, aesthetically clear solar cell that we did before? And so we started designing and synthesizing new molecules where we can make this system transparent as well, where it's not only absorbing outside of the visible part of the spectrum, but it's also glowing outside of the visible part of the spectrum. And so this has been getting a lot of attention. We had a couple of our articles on this pioneering work in Advanced Materials Journal's covers. So we'll talk more about this at the Innovation Celebration. I'll just acknowledge the group. We have a growing group of graduate students, postdocs, and visiting researchers. We have about a dozen. We also have about 8 undergraduate students that are actively working on a number of these projects. And I really want to highlight a few names here. One in particular, John Suttard, who was the Goldwater Scholar last year and was an NSF Graduate Fellowship recipient this year. He's been doing excellent work and been working on these transparent photovoltaic applications. So the undergrads really can do exceptional work. So we have a full range of exceptional students here. We have a number of funding sources, NSF, DOE. We have a lot of partnerships with companies like DuPont and BASF. So we're very thankful to all of our funding supporters. I'll also just highlight that we, as I mentioned, have been getting a lot of attention. One of the ones that I'm most excited about was the Spartan Wills commercial. So if you watch the Spartan Wills commercial during the basketball games, you'll see myself and one of my students on there. The other thing that was very exciting was that our work was highlighted as one of the top 5 reasons why 2014 was actually the year of the Spartan. So thank you for your attention. I'll take any questions that you might have.